And we're at video number 4. This is going to cover chapters 1.2 in the book from openstacks.org, and I will have a link in the description below. This is pages 30 to 44. Now, guys, the page numbers, if you're reading the PDF online, the PDF numbers are different from the page number. This is the page in the book. This section is going to cover exponents and scientific notation, and like I said, there will be a link below to the book, and there will be a link to your lecture notes printable if you want one of those. The lecture notes, we're going to start off with the exponents, and there's a place for you to write the answers to these sample problems right here. Let's jump in. There are 7 rules about exponents that we're going to talk about. What I want to do first, I want to take a minute and I want to go through and expand each one of these rules, and I want to show you where they come from. I don't want this to be something mysterious that you think you have to memorize, because really you don't. All these rules is a shortcut, and I know y'all love the shortcuts, but these are just shortcuts that people figured out after doing exponents over and over and over. These rules keep you from having to expand these out. For example, our very first rule is the product rule, and you can see it on your note sheet. A to the m times a to the n is equal to a to the m plus n. Now, we've already talked about the fact that an exponent tells you how many times to multiply that base together. So let's just look at what happens when we expand this out. What is x to the second power? That tells you to multiply x times itself 2 times. X to the third means multiply x times itself 3 times. Now, backing up, an exponent tells you how many times to multiply a base together. So if you have a base already multiplied, you can shorten it by using an exponent. How many times did I multiply this x together? 5. Well, we notice that, you know what, if you add the exponents together, you get 5. And that happens every time. So instead of having to write it out like this every time, you can just add that, usually in your head, and get the correct answer. So that's the first rule of exponents. If you have 2 bases, 2 exponents, you can just add. Your next rule is the quotient rule. Quotient means a fraction, so this is what happens when you have exponents in your fraction. Now, given we're talking about matching bases in all of these, what's going to happen when I expand this? And like I said, we are deriving the rule. I'm going to show you how the rule works. X to the 5th meant x 5 times, and x to the 3rd meant x 3 times. Now, what happens when you have a number over itself? You get 1, right? So these cancel out or divide out to make 1. Now, what do you have left over? On the top of the fraction bar, you have x squared. Notice your answer went where the largest number was. If you have more numbers on the top, then your answer is going to stay on the top. And instead of adding, like we did with multiplication, you can just subtract. Now, I do want to look at what happens if the scenario is reversed. What if you have a smaller number on top? Technically, you're still going to you can still subtract the exponents, but this is what happens. You've got 3 on the top and 3 on the bottom. Oops, 5 on the bottom, sorry. So these 3 are going to cancel out. Now, what do you have left on the bottom? You've got that x squared. Well, what's on the top? Well, all of these divided out to 1, so 1 times 1 times 1 gives you 1. So subtract no matter what. Just subtract the small one from the large one, and then put your answer on the same side of the fraction bar as your largest exponent. So I would do 5 minus 3, and my answer goes on top of the fraction bar, or it's a whole number. Here, I still do 5 minus 3, but just put your answer on the bottom where your largest exponent is. That way you never have a problem. The next rule is called the power rule, and it's when you have an exponent raised to another exponent. So notice, in this one, I have one base with two exponents. In the first example, I had two bases with two exponents. So now we have one base with two exponents. Now when we expand this one out, what I actually have is x to the third times x to the third. If I continue to expand that out, what do I have now? X to the sixth. And we figured out by doing this over and over and over that, you know what, every single time you could just multiply those two together. So two bases, two exponents, you're going to add the exponents. One base, two exponents, you're going to multiply. And we get x to the sixth. Okay? The next rule is a really simple one. It's called the zero exponent rule. And it says whatever you have, if it is raised to an exponent of 0, it is equal to 1. I don't care how atrocious that base looks. If it's got a 0 for an exponent, it's equal to 1. And I can show you why this is. I said I was going to expand these out. Let's just say I have x to the third over x to the third. What do you do with those exponents when you have a quotient like this? You're subtracting, right? So what is my exponent? 3 minus 3 is 0. So the reason x to the 0 is equal to 1 is because of where that 0 exponent came from. And it came from when you had matching numbers over each other, which as we all know is equal to 1. So now you know why x to the 0 is equal to 1. Shouldn't be so much harder to remember it. But I don't care what it looks like. If I've got negative x to the third, 1/2 b, 3.7 to the 0 power, it's equal to 1. This next property is your negative exponent rule. Now I just showed you how to subtract the exponents and always put it where the bottom one is so you don't have a negative exponent. But if you do, that's really just a symbol. And what that tells you is whatever number is raised to a negative exponent, it's on the wrong side of the fraction bar right now. So all you have to do to make that negative positive is put the whole thing on the opposite side, wherever it is. If I have 5 to the negative 2, that actually means 1 over 5 squared, which would be 1 over 25. If I have 1 over 3 to the negative 2, it's on the bottom now. So the way to change that exponent to a positive is to move it up to the top. So this would be just 3 squared over 1, which is 9. Now we have the power of a product rule. Think of the words. What's product mean? Multiply. So here's our product. We have two numbers multiplied together and we have them raised to a power. What this just tells you, and these are inside parentheses, is that every factor inside the parentheses gets one of those exponents. So if I have 2x to the third, that means 2 to the third, x to the third, which would simplify to 8x to the third. Everything in the parentheses gets one of those exponents. This is your power of a quotient rule, and it's pretty much the same thing as power of a product. If you have a fraction inside parentheses and an exponent outside, everything in the parentheses gets one of those exponents. So, for example, if I have x over 3 squared, that's x squared over 3 squared, or x squared over 9. And I'm going to work some examples of all these in just a second. We're just going over the rules first. Let's practice some. This is example 6 on page 35. Problem A says b to the second times b to the negative 8. Now when we have two bases and two exponents, we're going to add the exponents together. So what is 2 plus negative 8? Well, it's actually b to the negative 6. Usually we don't consider things in simplest form if the exponent is negative. And what did we say about a negative exponent? It means move that base to the opposite side of the fraction bar. So your final answer here is going to be 1 over b to the 6th. Now let's look at problem B. Negative x to the 5th times negative x to the negative 5. Well, that looks pretty atrocious, but it's really not so bad. You see your bases match here. So you have 2 bases and 2 exponents, and you can solve that by adding your exponents. Now your base is not going to change. So I'm still going to have negative x for a base. What happens when you add 5 plus negative 5? What do you get? A big 0. And now we have another rule that comes into play. Your 0 exponent. What is anything raised to the 0 power? 1. Wasn't so bad. Let's go for problem C. We've got negative 7z over negative 7z to the 5th. Now we had a product rule that said when you have the same the same bases as a fraction, you can subtract the exponents. Well, I don't have an exponent up here. Or do I? Can I not put this in parentheses and give it an exponent of 1? So it's just something you do in your head. Now, I'm going to subtract the exponents, and my answer is going to go where? Where the largest exponent is, so it's going to go on the bottom. It's going to leave me a 1 up here. Now down here, I'm going to have negative 7z to the what power? Well, 5 minus 1 is 4. These are the problems in example 9, page 37. These are just going to be a combination of all the properties and rules, so should be interesting. If I were you, I would pause the video at each problem and see if you can work it out. That way you get a little bit of extra practice and then a little reinforcement if you got the incorrect answer. Okay, so I have 6m to the 2nd n to the negative 1 all raised to the 3rd power. The first thing I need to do is get rid of those parentheses, and I do that by giving everything in here, every factor, a cube exponent. So what I have here is 6 to the 3rd m. Now what do you do when you have an exponent inside and an exponent outside? You multiply. So 2 times 3 is 6, and negative 1 times 3 is negative 3. So here's what I have now. Now let's clean this up a little bit. 6 to the 3rd power, we're just going to leave that here right now. You can do that on a calculator if you want to simplify that. M to the 6th is fine, just like it is. But you don't like to leave a negative exponent, so what you'd want to do there is put your n on the bottom, and the exponent changes from negative to positive. Example B says 17 to the 5th times 17 to the negative 4th times 17 to the negative 3. All matching bases, all multiplied together, so we can use the product property, and we can just add these exponents together. Now, 5 plus negative 4 plus negative 3 is going to be 5 plus negative 4 is 1 plus negative 3 is negative 2. So I have 17 to the negative 2. Once again, you don't like to leave a negative exponent, so you could put 1 over 17 squared, and I think that's 289. Let's go to problem C. U to the negative 1v over v to the negative 1 all squared. That's a lot. But remember, you only need to deal with one number or two numbers at a time. So let's just start dealing with them. U to the negative 1 squared. When you have one base with two exponents, you're multiplying. So what is negative 1 times 2? It's going to be negative 2. Now this v, what exponent does it actually have? Well, it's actually got the understood 1, if you want to do it that way. But 1 times 2 is 2, so now we're going to have v squared. Alright, now don't forget, the one in the bottom also gets one of these exponents. So v to the negative 1 times 2 is going to be v to the negative 2. Okay, now we got rid of parentheses. Let's see if we can clean this up a little bit. U to the negative 2. When you have a negative exponent, that tells you to move it to the opposite side of the fraction bar and make the exponent positive. So now we have u squared. V squared over v to the negative 2. These bases match. What do you do when you have matching bases in a fraction? You subtract. So what do I want to do here? 2 minus negative 2, which gives me 2 plus 2, so that's 4. And it's going to stay on the top because that's where the largest exponent is. And just for the sake of argument, let me show you that there's not just one way to do these. You can get your own system going. Let me back up right here. Let me show you another way that you can look at this. Now u to the negative 2, that's still got to go to the bottom. You could have looked at this as v to the negative 2 needs to go to the top. So it's going to go up there and be positive, and I still have the v squared up there. So now I'm adding exponents here, and I get this. You get the same answer, okay? I just want you to see there's different paths. You know, your way is not wrong if you do it different from me, as long as you can justify what you did. Problem D, let's see what we have here. We've got negative 2, a to the third, b to the negative 1 times 5, a to the negative 2, b to the second. Got two big factors included in parentheses. Here's where those properties are going to come in handy. The property of multiplication says if you've got all numbers multiplied together in two sets of parentheses, you can drop the parentheses. In other words, you're distributing a 1. So what we actually have here is all these numbers multiplied together. So let's start grouping things that match. What if I said, okay, negative 2 times 5, what is that? Negative 10. And I just got rid of those two. Now here, a to the third times a to the negative 2, what do you do when you have two bases and two exponents? You add the exponents. So that's going to be a, 3 plus negative 2 is 1. You don't have to put the 1. Next we have, let me cross those out. Next we have b to the negative 1 times b to the second. Well, what do you do when you have two bases and two exponents? You add the exponents. What's negative 1 plus 2? It's 1. So there's your final answer. And see that I didn't even have to have a step in here to work it. So it looked pretty bad at the outset, but it wound up not being much. Okay, example E. This looks horrendous. X squared times square root of 2 to the 4th power times x squared times square root of 2 to the negative 4th power. So back up and look at what you have. First of all, you notice these two things match. So we're not going to start trying to distribute in here. We're just going to consider this as one big base. Okay, since they match, they're the base. What's your exponent? 4 and negative 4. So when you multiply two bases together, what do you do for the exponents? You add. What is 4 plus negative 4? 0. And what is x to the second square root of 2 to the 0 power? A big 1. See how easy that was? Now example F, this is our last example, so hang in there with me. We have 3w squared to the 5th power over 6w to the negative 2 squared. Now there's not any cute little things that are going to make this all disappear. We're just going to have to plow into this and take care of our exponents. So first of all, let's just look at the top. We've got 3w squared to the 5th. This is going to simplify into 3 to the 5th. And w, what do you do when you have a base with two exponents? You multiply. All right, down here on the bottom, we have 6 squared. And then w, what's negative 2 times 2? Negative 4. Now let's take care of the 10 and the 4 first. I'm going to leave 3 to the 5th and 6 to the second as they are for now. When you have a negative exponent, what do you do to make it positive? You move it to the opposite side of the fraction bar. So now up here I have w to the 10th and w to the 4th. And how would you simplify w to the 10th and w to the 4th? You add the exponents. So at this point I have 3 to the 5th, w to the 14th over 6 squared. Now to take care of the math part. 3 to the 5th is 3 times 3 times 3 times 3, 5 times. So that's going to be 243 W to the 14th over 36. And this will also reduce down. 9 will go into both of those. And when you divide both of these by 9, you get 27 over 4. And that is all of our exponent examples. So let's move into scientific notation real quick. Our next topic is scientific notation. So what is scientific notation? You've all seen this in your science classes. And you know, that's what always amazes me, because they teach you this in like one day in a math class somewhere. And then you get to science and they expect you to know all about it. So we've started to get a little more intense with it in math, because we want you to be prepared when you go to your science class or your chemistry class, and you need to be able to work with these numbers. There's a lot more to scientific notation than just putting it in scientific or back into standard. There's way more. So let's get into this. Scientific notation, it looks like 3.7 times 10 to the negative 4. It's a way for us to write really big numbers in a more condensed format, because when you're copying things over and over and over, you can lose numbers if there's a big string of them. So anyway, there are some criteria about scientific notation. It takes the format of some number times 10 to an exponent. Now what about this number? Well, the absolute value of this number. Now pay attention to that. The absolute value. It doesn't mean that A can't be negative. A can be negative. Don't let anybody tell you that it can't be negative, because I've actually heard teachers say this number can't be negative. It can. But the absolute value of it has to be 1 is less than or equal to it, and 10 is greater than it. So it has to be in between 1 and 10. It can't even be a 10. Also, n has to be an integer. Now, we talked about number sets back in video number 1, so you should know what an integer is by now. So first, let's look at just changing some numbers from standard to scientific, or from scientific to standard. Now, this is based on the fact every number has a decimal. 7 has a decimal. Where is it? It's at the end. If I wanted to put 7000, I could. The decimal is there, we're just not showing it every time. What happens to a decimal when you multiply it by 10? You move your decimal over. If you multiply by 100, you move it over here. So if you multiply by 10 to the 5th, you're going to move it over to the right 5 times. What happens if your decimal is negative? You move it to the left. Let's go through example 11 on page 40 in your textbook. Problem A is 3.547 times 10 to the 14th power. So I'm just going to recopy the 3.547 here. This is scientific notation. I know that because it's got 10 to a power. Also, how do you know where to put your decimal? Well, you always want one digit to the left of the decimal. That's what that rule about A has to be between 1 and 10. It's one digit, because it's not quite 10, but it can be anywhere from 1 all the way up. So you're only going to have one number, one significant number to the left of your decimal. Alright, now since this is a 14, what I'm going to do is go where my decimal is right now, and I'm going to move it to the right 14 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then I'm going to fill in all of these with zeros. This would be standard notation of this number. So now you can see the benefit of scientific notation. It's a whole lot easier to write this out than it is to write this, because now my decimal is down here. So I would erase that decimal, and I guess I could put a comma there if I wanted to. Okay, so that was example A. Now example B is -2 times 10 to the 6th. Okay, where is the decimal right now? -2, the decimal is right there. It's at the end. Even though that 2 is negative, your decimal is at the end. So I'm going to move this over 6 places. 1, 2, 3, 4, 5, 6. And I'm going to fill in all these with zeros. So now, that's my number. This is standard notation from Scientific. Problem C says 7.91 times 10 to the -7. So once again, I'm going to start with 7.91. Now this has a negative exponent. So for negative exponents, you go the opposite direction. If you can't memorize this, just think about it. A -7 means you are dividing. Okay, because actually you would be putting this over 10 to the 7th and then you would divide. What happens to a decimal when you divide by 10? That number gets smaller and smaller and smaller. So what's going to make this number smaller? If I move it to the right, that number gets larger. But if I move it to the left, the number gets smaller. So let's move it to the left 7 times. 1, 2, 3, 4, 5, 6, 7. So here's my new decimal. And I'm going to have zeros in all of these places. So my new number looks like this. Example D says -8.05 times 10 to the -12. And once again, just because this number is negative, it doesn't mean anything. So we're going to start with -8.05, and we're going to move the decimal to the left 12 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's my new decimal. And I would have to go back and put zeros for each place. So that's going to give me a new number of, let's see, 4, 5, 6, 1, 2. And it's -805. Okay. Let's look at example 10 on page 39. We're going to pick out 2 problems, the A and the D problem. And we are given 2 numbers in standard form, and we want to change these into scientific notation. The first thing is to find the decimal part of it. And you want to put your decimal so that you have the number to the left of the decimal is between 1 and 10. So my decimal is going to go right here at 2.4. That's how you figure out the first part. That's the hardest part, because it's going to be times 10. Now we have to figure out the exponent. Where is your decimal right now? It's way down here. So when you move the decimal to the left, your exponent up here is going to be positive, because what you're going to write right here has to be equal to this. So what would you do to this number if you wanted to recreate your original? Well, you would want to get a bigger number, right? So you're going to need a positive exponent. Now let's see how many spaces it's going to take us to get all the way down here between the 2 and the 4. Now the biggest mistake I see is people will stop right here. Remember, your number, your A right here has to be between 1 and 10. So let's count backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So it's going to be 2.4 times 10 to the 22nd power. Now let's look at example D. First, figure out your A, your number. Well, I don't want to put it here because 0.94 is less than 1, and my A has to be between 1 and 10. I don't want to put it here because 94 would be larger than 10. So that's why you choose to make it 9.4. That's your first decision. Now that you've made that decision, all you have to do is count the spaces from where the decimal is to where you just ended up with it. So if we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I went over 13 places. Now I want you to just look at this. If I multiply 9.4 times 10 to the 13th power, I'm going to be adding zeros to the right, and that is not my original number. That's how you can tell that should have been negative, okay? Because I moved the decimal to the right to transfer it from standard to scientific notation. Now let's look at some operations with scientific notation. This is where it gets a little bit intense. We're on example 12, page 41, and this is problem A. We have 8.14 times 10 to the negative 7 times 6.5 times 10 to the 10th. Now, the problem is if you put this in the calculator, it's just going to give you a number. And our directions say put your answer in scientific notation. While you are going to want to use your calculator at some point through this, doing the whole thing in a calculator actually takes more time to punch in all the numbers than just to do it in your head. So let's just dig in. What you actually have here is 4 numbers multiplied times each other. And you wouldn't want to write this out every time, but I just want to show you what I mean. We can write this just like this. This is just 4 numbers multiplied together. So now let's group numbers together that are convenient. And by convenient, I mean we have 2 numbers here that have exponents and matching bases. So let's put them next to each other. So now I'm going to put 8.14 down here times 6.5, and then 10 to the negative 7 times 10 to the 10. Okay, 8.14 times 6.5, that's a calculator problem. And I get 52.91. Alright, now what is 10 to the negative 7 times 10 to the 10th? Matching bases, add your exponents, so you get 10 to the 3rd power. Okay, but that's not your answer, because this is not in scientific notation. Why? Why is it not? Because this number is 52. It's not between 1 and 10. So here's where you have to do some adjusting. Where do I need this decimal to be? I need the decimal to be over here. I need for this number to be 5.291. Now what's that going to do here? Well, I moved it to the left once here, so I'm going to have to raise this by 1 power. Okay, let's look at problem B. This one is division. So let's see what we're going to do here. What I'm going to do first of all is I'm just going to rewrite this in fraction form. And it's going to look like this. So once I have it in fraction format, I'm going to work this part and then this part, okay? When you put this into the calculator, 4 divided by negative 1.52, you're going to get 2.63157897. That's a really long number. So we're just going to round that off to 2.63 right now, and it's going to be negative because a positive divided by a negative is negative. So I've got 2.63 times 10. Okay, 10 to the 5th over 10 to the 9th. What is that? You're going to subtract your exponents. 5 minus 9 gives you 10 to the negative 4. What if you did the thing about subtracting the large one from the small one? Well, if you did 9 minus 5, you're going to get 4, and where's that going to go? It's going to go where the largest exponent is. So if you did it that way, you would start off here with 10 to the 4th on the bottom, and in scientific notation we don't divide by 10, you change it to multiply by something with that negative exponent. So I just want you to see, as long as you adhere to your math rules, you're still going to get the right answer. It doesn't matter which part you do first. Check this number. Be sure that the absolute value of that number is between 1 and 10. And it is. So this is final answer. Example 12, page 41, number C. We've got 2.7 times 10 to the 5th times 6.04 times 10 to the 13th. This would be a really good one for you to pause the video right here and see if you can work this problem out before you watch me do it. Anyhow, just like on the other one, we're going to commute these numbers and put similar things together. So I'm going to put 2.7 times 6.04 together, and 10 to the 5th times 10 to the 13th. All right, multiplying 2.7 times 6.04 gives me 16.308 times 10 to the 18th. Now once again, the problem with this, see that was easy, but it's not in scientific notation because this number is not between 1 and 10. So I have to move my decimal one place to the left. That's going to give me 1.6308. And since I moved it 1 point to the left, I need to increase my exponent by 1. So 1.6308 times 10 to the 19th. Problem D from example 12. This one is division. So what I'm going to do is put 1.2 times 10 to the 8th on top of 9.6 times 10 to the 5th. Then I can regroup just like this and simplify. So when I do 1.2 divided by 9.6, I get 0.125 times, right here I've got 10 to the 8th over 10 to the 5th. So I'm going to subtract exponents. 8 minus 5 gives me 3. All right, now I have 0.125 times 10 to the 3rd. Once again, this is not scientific notation. I need to move my decimal over. This needs to be between 1 and 10. So I'm going to need to move my decimal to the right once to get 1.25. Now since I moved it to the right once, that means I already multiplied by 10 one time. So I'm going to reduce this. Okay? So look at it. If 0.125 times 10 to the 3rd is right here, well if I make this bigger, this has to be smaller. Okay, here's our last one. This is example E, or part E from example 12. Now this time I have 3 scientific notation terms multiplied together. But it's the same thing, it's just 3 of them. I'm going to take out all of the first numbers and multiply them together, and then I'm going to multiply all of my tens together by adding exponents. So I'm going to have 3.33 times negative 1.05 times 5.62. Then all of that is going to be times, let me put it like this, 10 to the 4th times 10 to the 7th times 10 to the 5th. Now how was I allowed to do that? By the commutative property of multiplication. So when you multiply these 3 numbers together, you're going to get negative, and of course, let me use a calculator real quick. And that gives you 19.65. Now multiplying all these tens together, 7 plus 4 is 11, plus 5 is 16. Okay, is this in scientific notation? No, why not? Well, this 19.65, its absolute value is not between 1 and 10. So my decimal is going to need to go to the left one time. And since I moved to the left, I'm going to raise my exponent 1. So now I have negative 1.965 times 10 to the 17th. Now let's turn over to page 42 and let's look at example 13. These are usually the problems I just kind of skip over. But, you know, in all honesty, these are the kind of problems that your standardized testing are focusing on these days, because they want you to be able to use the math, and this is a use problem. A lot of times you know how to do the math, but you don't know how to get the math. So let's look at this problem. In April 2014, the population of the United States was 308 million people. The national debt was about 17,547 and 369 zeros. All right, we want to find the amount of debt per person. So if this is the debt, this is the number of people, what operation do we need to do there to sort that out? Well, you're going to use division. We are going to divide this 17,547, 2, 3, 4, 5, 6, 7, 8, 9 by the number of people that owe that money. So that's going to be 308, 1, 2, 3, 4, 5, 6. Now those numbers are so large, most calculators don't have enough digits to put this in. So once again, it's just going to be more trouble to do it on a calculator than it will be to do it using scientific notation. So let's see, if I change this to scientific notation, first of all, what's this going to be? Where am I going to put my decimal? Right here between the 1 and the 7, because I want 1.7547. That number is between 1 and 10, isn't it? So that's your guideline. My first number needs to be between 1 and 10. So I'm going to rewrite that as 1.7547. Now let's see what exponent of 10 we need. Well, if my decimal is here, I went backwards, I went to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. Now do I need a positive 13 or a negative 13? Since I went to the left, I'm going to need a positive 13. Just think of it. I need for this number to be able to represent this number. If I use a positive 13, what's going to happen to this number? It's going to get larger. Well, the original number is a lot larger than 1.7, so that's what I need. All right, now let's look at 308. Same thing. Where do I put the decimal? It's going to need to go right here after the 3. So I'm going to put 3.08 times 10 to the. Where's my decimal now? It's right here. So how many times did I go to the left? 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8. Now, this is a whole lot easier to simplify. So if I do 1.7547 divided by 3.08, I get 0.5697, and we'll round it off there, times, all right, what do you do here? Subtract exponents, because you have matching bases in a quotient or a fraction form. So I'm going to do 13 minus 8, which gives me positive 5. Now, is this in scientific notation? No. We're going to have to move this over to the right one time. So it's going to be 5.697 times 10. Now remember, since I moved it to the right once, what I actually did is I already multiplied it by 10 one time. So that means I'm going to need to multiply it by 10 one less time. And we're not quite finished, because the directions tell you to put this in standard notation and in scientific notation. Well, here's scientific. So to go standard, well, if you multiply times 10 to the 4th, you're going to go over 1, 2, 3. I need one more. Let me just do this. 5.697. If I move over 4 places, 1, 2, 3, 4. I need one more 0. So that means $56,970. That is the amount of debt that each person in the United States has as of 2014. So that was even a long time ago. So wrapping it up, your links to the book are in the description. Your link to the to my lecture notes are in the description. In your book, on page 43 and 44, that's where your exercises are. I'd really like for you to work through, these. At least do the odd ones and check your answers in the back of the book. Remember, when you do your work, when you do these assignments, this is your opportunity to ask me questions about what you don't understand right now, not 3 months from now when you're taking a test and you don't know how to work anything. So do it one thing at the time. So give it 100% and let me know if you have any problems. And I will see you in video number 5.